Right, shall we get started?
Big day.
Big day. So, welcome everyone to today's Tao seminar. It's a great pleasure to welcome one of our own, Stephen Schwartz, here giving today's lecture. Yeah, that is because we both taught, and I'm still in the teaching mode with him, it seems. Today's Tao's lecture, and of course, many of you know Steve, but it's good to go over his, scientific career, long-lasting career. Some things you may not know. So Steve got his bachelor degrees in chemistry at Harvard. Then he did his physical chemistry in PhD in physical chemistry at Berkeley. So went from the East Coast to the West Coast. Then I didn't know that you were a Fulbright postdoctoral fellow and a Ramsay Memorial Fellow at University of Cambridge. So lived in Cambridge for almost 2 years. And then here's maybe a big surprise. He joined Stony Brook Chemistry Department as a faculty for about 6 years. And then moved over to Brookhaven National Laboratory, where he had a very, very distinguished and long 40 years or so career. Currently, he is the senior scientist emeritus from the BNL, and of course, our adjunct faculty. He served 2004 to 2009 as the chief scientist of the atmospheric science program of the United States Department of Energy. So all funding in this time for aerosol and cloud effects went through Steve's desk. A couple of awards, of course, he has so much. Don't want to talk here 10 minutes. Some things to say is, of course, fellow of the American Geophysical Union, a fellow of the American Association for the Advancement of Sciences, a fellow of the International Union of Pure and Applied Chemistry. He recently was named International Aerosol Fellow. That was the most recent one. Already in 2006, he was named ISI, so Web of Science, highly cited researcher. And I don't know, you are now above 25,000 citations or something like this. Steve has published more than 140 articles, books, proceedings, reports. Something I want to point out, and then I'm finishing, because there's relation to our department. In 1992, had kind of a groundbreaking article with Carlson, James Hansen, who was the NASA GIS director, who testified before Congress, and our Bob says, provided the first global scale estimate of radiative forcing due to anthropogenic sulfuric aerosol. And I think that's still your most highly cited publication. And with that, I stop, because I could go through pages and pages. We are very happy to have you here. And the title of your talk today is Observational Constraint Model for Uptake of Excess Atmospheric CO2 by the world ocean in praise of simple models. Nothing is simple in science, but we hope that is a simple model. Thank you, Steve.
Well, thank you, Daniel, for the gracious introduction. Thank you to SoMAS for hosting me and the adjunct faculty. It's a very nice place to be. It's an intellectually stimulating place, and I even got to co-teach a course with Daniel on atmospheric aerosols. A couple of the students from that course I'm pleased to see are here, who will, I hope, come to think that maybe I know something beyond atmospheric aerosols. So as Daniel mentioned, I've done a lot of things over the course of my career. It's been a lot of fun. And this is a new venture for me into atmospheric CO2. And I think I have some things to say in praise of simple models. And why do we want simple models? Really, they enhance understanding. You can look inside a simple model that has transparent walls as opposed to opaque walls. And we can see what's going on in the model. We can change things around and see what happens when we change things. So that's what I like, a simple model. And simple models stood me well in my career. Another subtitle of this might be "What's Steve been up to in the past few years?" So I'm happy to share that with you. So on.
Maybe click on the slide. Maybe you have to click once because I was in the Zoom menu. So click back, maybe now it should work.
That should work.
Yes.
Okay. I want to start with some things you already know. That's a good way to start a lecture. One of the most important data sets of the 20th century, certainly in atmospheric science, is what's come to be known as the Keeling curve. Dave Keeling, shown here, started measurements in the late 1950s. He did a back of the envelope calculation. How much carbon is human society burning? And if you put that in the atmosphere, what would the increase concentration, ppms, mixing ratio, increase be? And he said, okay, let's make a machine that's 10 times more sensitive than that so we can try to measure this and do it with some accuracy and some precision and see what's going on. So what's commonly shown is the Keeling curve, the increase over this period of time from something like 320 up to something like over 400 parts per million, million molecules of dry air. 400 of them are CO2, but it started out lower, and this is when he started making the measurements. Other thing that's very interesting in this is the annual cycle, and it repeats and it goes up and down, and that's well understood or well attributed to uptake by the terrestrial biosphere during the summertime, drawdown of CO2, and then comes the winter time, the release of CO2 back into the atmosphere, and it's very well known. I want to change the scale so that I can go back in time to pre-industrial. We're going to call that 1750, and then put onto this curve measurements by David Etheridge and colleagues in Antarctica, ice cores in the glacier and in the firn, ice cores which, like tree rings, you can count them and you know how many ice rings you have annually, and then you can get the age on that with quite good precision, and then get the CO2 concentration as a function of time, starting out here at 278, and that's what we commonly take as pre-industrial, increasing with time, and then a perfect match to the measurements in air started by Keeling. Well, maybe not quite a perfect match. There's a little bit of difference. Why? Keeling's in the northern hemisphere, Etheridge is in the southern hemisphere. Most combustion is in the northern hemisphere, southern hemisphere lags a little. Again, there's a signal in that which you can then try to confer timescales of atmospheric mixing between the two hemispheres. It's a rich data set and enhanced then by the ice core measurements. Another hero in this business is a man named Greg Marland, and he's, over his career, has done systematic inventories of how much carbon is being burnt by fossil fuel combustion, and that puts the CO2 into the atmosphere. That's what we call emissions into the atmosphere. And if you look at the scale, we're talking, well, units first. My students know that I pay a lot of attention to units. Petagrams per year, 10 to the 15th grams per year of carbon. And that's the unit that we're going to use throughout the talk. And that's the unit that's used throughout the community. And so what he has done is then inventory, country by country, industry by industry, what are the sources of carbon. Hard to see these numbers. I apologize, it's his figure. Here's 1950, here's 1750, nothing going on really. 1850, just a little bit, then increasing to the present time, shown here is 2017. And black is solids, call that coal. And coal was the fuel of choice. Liquids, gasoline and other liquid fuels, diesel, really didn't take off until something like 1950. And What? Putting cars and trucks on the road. So that's what that is. Then you have natural gas that comes in, and there's cement manufacture. You take limestone and you heat it, and the CO2 comes off. It's a little bit of an add on to that. Total these units is something like roughly like 10. So that's a number that's going to be important to us. And this man really devoted his career, another hero in our business. Here's another hero in our business, a man named Richard Ski Houghton, formerly at Brookhaven. And what he has done is similarly inventorying emissions from what is called in the community land use change. You're deforesting, the carbon goes into the atmosphere, what fraction goes into the atmosphere, inventory, painstaking inventory, country by country, areas. You have here North America, and that's an interesting one. The units, by the way, petagrams of carbon per year, same as we just had. The numbers, not the same on each chart. So this one goes up to about 1 petagram per year. The previous one was up to about 10. So it's a small fraction. Here's global up to something like 1.5. Negative numbers. What's negative number? That's called afforestation, opposite of deforestation, where you're growing trees where there was previous land cleared, and so you're taking carbon dioxide out of the atmosphere and putting it into tree trunks. Europe, a lot of that, relatively, it's a much smaller number. Here's 0.4, here's 0.05. Then here's global up to something like 1.5. The total shown here, this one in green is the land use change emissions with uncertainty bars on it. This one in red took off a lot later. 1850, you're starting to get the burning of coal, but has increased greatly, fossil fuels. And then the total, which is shown there in black with the uncertainties associated, added uncertainties from the two. What came as a surprise to me when I first plotted this up is that these curves really don't cross until something like 1950. So after what our generation says, after the war, after World War II, there was this great increase in industrialization and the combustion of fossil fuels. And these curves don't cross until something like 1950. Looking more at the picture, this is now cumulative emissions. Add up next year's to the previous one, added up. That's cumulative emissions. So the same color scheme. The green is the land use change. Get used to these buttons. The red is the fossil fuel, and the black is the total. Total up to something like 600 or 700 petagrams, not per year, petagrams. And again, when do these curves cross? They don't cross until something like 1985. It's much later than I would have thought in terms of the fossil fuel contribution to the total in the atmosphere. Moving forward now, same scale. Here's 600, 700. Here's the curve we just saw for the total. Here, in the same units now, we know how to convert parts per million in the atmosphere of CO2. We know how to convert that into grams into petagrams. Here's the measurements that we've just been looking at. Here's the total emissions. Where does the rest of it go? And that's the question that our community is asking in a qualitative and a quantitative way. It's drawn down. There's only two places it can go, the ocean and the terrestrial biosphere. It's drawn down into those two compartments of our carbon dioxide system. This difference has been called nature's subsidy of our CO2 habit. And then we want to understand our objective the community's objectives to understand this diagnostically and prognostically. So now I get to the rough outline of the talk, and I can see we're not going to get everything done. Well, I want to talk at some length about the carbon budget. So this estimates of the fluxes between compartments and the transfer coefficients describing those rates.
Actually, I have a question about your previous slide. When you say the difference part of it is from the terrestrial biosphere, but wasn't a major part of that has been attributed as land use change already?
The land use change we're taking into account on the emission side. So the land use change is included already. Where's up in here? So this, and we'll talk about it more. The difference includes drawdown, but not the change. I'm glad you asked, so I can clarify that. And then there's also the drawdown into the ocean. And I'll call it net drawdown because individual molecules exchange very rapidly. So we talk about the net. Then I'm going to introduce and talk some about my three compartment model, a simple model that I introduced into this discussion. Simple in that we're not calculating the atmospheric CO2. We're using the measurements of atmospheric CO2 to drive the differential equations that comprise the model. So we don't have to calculate how much is in the atmosphere. What we're interested in is how much is drawn down into the ocean. When we get done, we can say, well, where's the rest go? And that's the net into the terrestrial biosphere, but we're not calculating that. So the approach then, and it's a novel approach, is to use the uptake of heat. What heat? The planet's getting hotter. Where's that energy going? Energy is going largely into the ocean. So we're going to use uptake of heat as a proxy for the uptake of any passive tracer. And then use that to quantify the exchange between the three compartments. What are the three compartments? Atmosphere, mixed layer, ocean, deep ocean. I'll talk about results from the model. We're going to define and evaluate a transfer coefficient. There's my chemical kinetics background. I did my PhD in chemical kinetics. I'm kind of surprised that the community is not looking more at transfer coefficients, and I'll try to make that evident. I will hopefully get to what I think is happening is a slight decrease in that, significant, appreciable decrease in that transfer coefficient from the atmosphere to the ocean. Try to understand the reason for that. In parentheses, what can we say using this model to, by difference, say something about models of net transport between the atmosphere and the terrestrial biosphere? I don't know if I'll get there. I'll try to summarize, and then I will have some concluding observations about models. Okay, global CO2 budget. You have your household budget. Your annual income and your annual increment in your net worth is your income minus your expenditures. And hopefully that's a positive number. And then your cumulative increase over your lifetime or over a period of time is the integral of that, the income minus the expenditures. And again, hopefully that's a positive number. Okay, same thing with CO2. We're interested in atmospheric CO2. The annual increase in the atmospheric CO2 is emissions minus sinks. Where are the sinks? Ocean, terrestrial, that's the sinks. And then the cumulative excess is how much we saw the increase in CO2 that was in the Keeling curve, that was in the increase over a period of time. So now we're going to try to get a quantitative understanding of that. This is another important figure historically, another couple of heroes in the business. Jorge Sarmiento, chemical oceanographer. Nicholas Gruber, I don't quite know how to qualify him. He does a lot in terms of oceanography. And this is from a paper that they had in Physics Today, of all places, year 2002. And I'm going to build this up. So this is, they're treating pre-industrial and then anthropogenic. On this slide, I have the pre-industrial, and that's in black. Some interesting numbers. Atmosphere, how much carbon is in the pre-industrial atmosphere? We know how to make that calculation with the pre-industrial CO2. Boom, done. How much is in the mixed layer ocean? We really don't know, but the chemistry is well understood. And the chemistry is well understood. It's interesting inorganic chemistry, dissolved in organic chemistry. A lot of people have really studied that to a gnat's eyelash. And you say, if it were in equilibrium, it would be something like 900. What are the units? Petagrams, petagrams. Then the flux between them. And this is kind of a guess, but it's a very informed guess based on rates of transfer of radioactive isotopes between the atmosphere and the mixed layer ocean, and then they decay, and what's the decay rate relative to the exchange back to the atmosphere. So you get a pretty informed view. And if you look at the numbers, and I hope they're visible, down is 70, petagrams per year, up is 70.6. Well, why? Because you have other pathways, you have weathering, you have carbon that goes through the rivers and gets into the ocean, and so that's adding on to this a little bit, going the other direction. So it's a slight disequilibrium. But the chemist looks at this, me, and says, boy, this system is in near chemical equilibrium. That's important. That really informs our thinking about it. Over here on the terrestrial side, units, the quantity is net primary production, net primary productivity. How much carbon is drawn down in the course of the year and how much goes back up in the course of the year. Those are these two numbers. And you look at them again, and they're very close to equal. Not a chemical equilibrium. It's a dynamic steady state. If we're chemical equilibrium, it would all be CO2. CO2 is the bottom of the energy well. And why is it not all CO2? Well, we have something called the sun that's driving a system that's very dynamic. So these are the best estimates from that time. They're still pretty good of those two numbers, again, approximately equal. And then based again largely on isotope work, flux going down from the surface ocean, the mixed layer ocean, into the deep ocean. And so that's the sense of this picture. And just again, looking at their numbers and their font, 90.2 going down out of 900. And so that's roughly 10% per year going from the mixed layer ocean into the deep ocean. Then important contribution, still the same paper. In red is the anthropogenic contributions at that time. Now remember, we were talking at our time of roughly 10 petagrams per year. At that time, it was roughly 5 petagrams for fossil fuel combustion. So I have to scale these numbers up. Again, calling attention. These two numbers between the atmosphere and the mixed layer ocean, they're about the same. 21 going down, 20 going up. There's a net flux downward. It's not big relative to the magnitude itself. A land sink of about 1.9, a land use change contribution to the source, not part of this, Edmund. Land use change emissions of 1.7, land sink of 1.9, atmosphere has grown over this period of time. There's an increase now in the stock of carbon in the deep ocean. A very insightful paper was taken over pretty much completely by AR4, fourth IPCC assessment report. Basically, the numbers are the same. Nothing is particularly changed except for the fact that they used gross primary. Go back. What did I do? Push the wrong button and held it. I'm in trouble.
Yeah, let's see. Right, for slight issue.
Let me see.
Go back.
Yeah.
Like the back arrow should work.
This.
Well, now you've all seen.
Yeah.
Fuck. There's no secrets anymore. There you go. We're good. So that's it. That's the one. Okay. Thank you.
Should be honest.
Okay. The point I was trying to make before I pushed the wrong button was that the one big change, and it's really no change whatsoever, is up here that they're using gross primary production instead of net. And everybody knows, it's a well-known fact, that gross is roughly twice net. Gross is roughly twice the net primary production, so they scaled it up by a factor of 2, but this is basically the same figure. What else did I want to say about that? You're done the end thing.
It's not working anymore?
No,
yeah.
it's not working.
Oh, yeah. It's like, may have to. Now it should.
There, okay.
Sorry about that.
Is this gonna work again? So the point I was trying to make is that it's. Be careful with what. No.
Yeah.
Pushing the run.
No, go forward.
And the gross primary production rather than net, that's the point of that next slide. That's the only point of that next slide. And I characterize these estimates as very informed estimates. And why? Because it really comes from the chemical oceanography community who are concerned with consistent pictures of the budgets of radioisotopes, which is a real tool for getting these transfer coefficients between the different compartments. One modification that I would make to that figure is it only had a downward component to from the mixed layer ocean to the deep ocean. There should be a return component, and that's being shown there. What? Again, as I'm saying, I'm surprised that the community has not introduced this concept of transfer coefficients. The quotient of the flux to the stock in the leaving compartment. And I mean, the stocks, the fluxes, they increase with time. So you have the carbon in the system. The transfer coefficients ought to be more or less constant. So taking those numbers, I just do a simple quotient and carefully. An 0.117, 12% per year from the atmosphere into the ocean as a transfer coefficient, as a what I will call a net transfer coefficient, a net transfer coefficient of about 10% per year from the mixed layer ocean into the deep ocean. So that's a nice way of looking at these things in terms of transfer coefficients. Transfer coefficients are, as we would say in chemical thermodynamics, intensive properties as opposed to extensive properties, which is the amount of stuff you got. Here we go now to AR5. they ruined a perfectly nice template of a figure from the AR4 going back to Sarmiento and Gruber and made it very complex, but then the numbers changed only ever so slightly, as is shown here. And I won't go into that. Now you go to AR6, and they just totally messed up the figure, and it's very hard to follow what's in the figure. But furthermore, hidden down in here is a transfer coefficient of something like used to be 10% per year, and is now 29% per year. And nobody seemed to realize or pick up on that. It's been recognized since. Okay, just to finish up and get ahead of ourselves, this is the budget that is determined in the present study. I used the Sarmiento and Gruber number for the transfer coefficient from the atmosphere to the mixed layer ocean. Then I examined sensitivity to that. I will show you how I came up with the transfer coefficient from the mixed layer ocean to the deep ocean, and that's perhaps one of the novel pieces of the present study, which after some period of time got published to my great satisfaction. Okay, here's the three compartment model. The atmosphere, the mixed layer ocean, the deep ocean. I'm pushing the wrong button. And transfer coefficients. And what do I need in terms of transfer coefficients? A transfer coefficient from the atmosphere to the mixed layer ocean to the atmosphere. They must be related. They're related by essentially detailed balance in chemical kinetics. We have the same thing from the mixed layer ocean into the deep ocean. It is forced by measured atmospheric CO2. There's two differential equations. Mixed layer ocean, here's a differential equation. Deep ocean, a differential equation. The up and down rate constants are related by the equilibrium requirement, by the steady state requirement. So it's two independent parameters to be determined from observations. The differential equations again, transfer coefficient from the atmosphere to the mixed layer ocean. It's what is called again in the trade a piston velocity, generally expressed as the rate of transfer on the water side of the ocean, and we relate that to the transfer coefficient in the atmosphere to mixed layer by the area of the ocean divided by the volume of the ocean. We're done. It's a little more complicated than that because solubility of CO2 is not linear. The more CO2 you put into the water, the less soluble it becomes. You have to ultimately get into what's called a differential equilibrium constant. For those of you who are familiar with it, it's closely related to the Revell factor. So that must be taken into account. Mixed layer to deep ocean, a piston velocity for transfer of heat from the mixed layer to the deep ocean, and then that's related again to that piston velocity by the depth of those two components of the ocean. The mixed layer ocean taken as 100 meters. How do I get that number, that latter number? That latter number is really important. It's the flux of heat is taken as proportional to the difference in temperature between the atmosphere and the ocean based on measurements. We don't have that difference, but we have that difference from the uptake of heat. And let me try to lead you through it. This one is well known. This is the change in temperature versus time. This one is from the GIFS compilation. Global heat content anomaly. There is a whole community that sets about measuring the heat content of the ocean. You measure the heat content of the ocean this year, you measure it again next year, you measure it again the year after. That's what's being shown here in this curve at the lower left. Units, watt years per meter squared. So it's watts per meter squared times years. So that's the units of that. For those who want to think in terms of SI units, it's in zetajoules. Zetajoules. So it's, there is community that thinks that way, and it's typically reported that way. And you can see this quantity is increasing with time. Here's for the mixed layer, and we calculate that with the assumption the mixed layer is in equilibrium in thermal equilibrium with the atmosphere. Here's the total, and it's going up to something like, from 1960 to the present, 40 watt years per meter squared. Well, how do they get the number? As I say, go out with buoys. They're now autonomous buoys. The so-called Argo system. They're programmed to go at depth, measure temperature at depth. From temperature and the heat capacity of seawater, you get a ocean heat content locally, integrate over the ocean. Tough job. Do it again next year and take the difference. So here's the total energy that's been taken up by the global ocean over this period of time. Here's the rate of change of that. It's the derivative of this one. First of all, taking derivatives of data is tough. Data is noisy. Data has fluctuations in it. By the time you take the derivative, it has big fluctuations in it. Second point, look at the magnitude. Its magnitude is something like 3-4 watts per meter squared. Doubling of CO2 is thought to be about 4 watts per meter squared annual increment of heat energy into the planet. We're not there yet. So 3 watts per meter squared, it's a reasonable number. And now, to get the transfer coefficient, you plot this one against this one, and these are the same quantities in the numerator, and you're plotting it now against the increase in delta temperature, and you get a slope and a confidence interval. Well, how much confidence do we have in the confidence interval? This is the number. This confidence interval is going to show up a lot in the rest of the talk. But look at the scatter on that. And then the question is that scatter real? Does the Earth's energy content per year really change that much from year to year? Or is it measurement error? Or is it the lack of sufficient coverage, spatial coverage of the ocean from year to year that gives you this number? It's a puzzle, we don't know. But this is the number that I'm going to use for my transfer coefficient, and I'm done. So I put the numbers in the differential equation, I solve the equation. Here is now the anthropogenic carbon stocks in the several compartments. Here, go back. Well, I won't try. I'll point to this upper left. Here's integrated emissions. Here is atmosphere. Here is terrestrial. Here is ocean with the uncertainty associated with it from the confidence interval from the calculated in the previous slide, and comparison with GCB 23, the global carbon budget paper that gets published annually with something like 50 authors, that is the summary of best understanding of the global carbon budget. And it agrees rather well. But that's the stocks. This is now the derivative. This is the fluxes. The fluxes, net fluxes between the compartments. Again, what's being shown here is now, this is the total emissions petagrams. This is petagrams per year. Here's the atmosphere. Back here, when the measurements were made in ice cores, it's kind of smooth. When the atmosphere is being measured year by year, it's kind of jumps around. Good question, why? From the ocean, that's rather smooth as calculated by the present model, and also as calculated, presented from the survey of the data by the global carbon budget community. And then terrestrial by difference. It's also possible to distinguish how much is in the deep ocean, how much is in the mixed layer ocean. The mixed layer ocean is a small fraction. It's just a transit regime where the heat then goes into where the carbon dioxide heat also goes into the deep ocean. Now the transfer, look at this, it's an extensive property, it's increasing. Here you're thinking you're doing rather well. Take the ratio of that to the atmospheric stock. That's the net transfer coefficient, the chemical kineticist wants that number. And that's pretty constant over this period of time. There are some fluctuations. My model is totally transparent. I know the reasons for these fluctuations. Here's the global carbon budget numbers, which don't agree in terms of the fluctuations. These fluctuations basically are responses to the derivative, time derivative of atmospheric CO2. That's it. That's why these fluctuations. So there's the findings in comparison with one survey. Here, there's a large community that runs models that try to calculate the net transfer, try to calculate the flux. I turn it into net transfer coefficient on different time scales. This one, push the right button, from 1880 to the present. I thought it was stupid. And you can see 10 such models, Earth system models, that are calculating this. Some simple climate models, some observations based on CO2 fugacity, some global ocean biochemistry models, units per year. So it's petagrams per year divided by petagrams. The units are per year. The magnitude, well, here's 2% per year, 0.02 per year. So that sets the scale. I would say these Earth system models, boy, they come out with the next global climate budget paper a year from now. And here's my model, and it moved a little bit, but it really doesn't. I'd go home to the spouse and say, is what I'm doing worthwhile doing? But this is what people are doing for a living, and they're getting these kinds of results. These are some, what I would characterize as observationally constrained models. One's based on from De Vries on the ocean circulation inverse model. One's based on a Green's function approach, and you can compare these, and they compare rather well without those large fluctuations from time to time. Those are all models. Models are plentiful. Measurements are sparse. There are some measurements. This is a set of measurements of ocean anthropogenic dissolved inorganic carbon surveys. You run a ship along on a longitude line, and you do CTB buckets and you measure, bring them up, and you get the number of the dissolved inorganic carbon. It's painstaking work, and it requires great accuracy. I see Steve Beaupre nodding his head on that. Okay. Then this is also compared to those models that I just mentioned. Gruber and his colleagues take a survey that's done that way 1 year, do it again 10 years, 15 years later, take the difference in order to get a net flux, which is shown here. And here's Gruber's measurements here as a survey a review by Graven. There's a set of measurements by the C-flux community. There's another set of measurements that are compiled by Mayo. And I would say the agreement is rather satisfying. Here's Takahashi's work, which some of you may know. Takahashi takes measurements of partial pressure difference globally over space, multiplies them by the wind speed dependent transfer coefficient to get a net flux. It is large positive someplace, large negative someplace else, does the spatial integration, and that's this number that comes across here with the large error bar. And I said that's futile. You just can't do an integration like that and get a meaningful result. Here's Wally Brook, another hero in the business, and he has ocean radiocarbon relative to 1955. Why relative to 55? This is the bomb carbon. Carbon 14 O2 is introduced in the atmosphere from weapons testing. You're producing N14, it's an NP reaction, it makes C14, it makes CO2. We have a pretty good inventory of that in the atmosphere, it can be modeled. These are just direct measurements in the ocean and now compared to what's calculated with the what I'm calling the 3C CDM, 3-compartment concentration driven model. And his line is the black one, which is shown here, and the 3C CDM is the blue one, which is surrounded by the light blue band. And I just was astonished when I made that plot as to how well they agree. So now we can answer the question. This is a cumulative plot. Where does the carbon go? Here's the amount that's in the atmosphere, fraction that's in the atmosphere, the fraction that's in the ocean, the fraction deep ocean, mixed layer ocean, terrestrial biosphere by difference. And the atmosphere is going down, terrestrial biosphere is going up. So there's some signal in there yet to be understood. I have maybe just enough time to talk about the decrease over time in the net atmosphere ocean transport coefficient. So this is what we've seen before in terms of net transfer flux. A bunch of models, the GOBM's Global Ocean Biochemistry model, and the 3C CDM. Here is the net uptake coefficient. This is over the Keeling era, 1959 to the present. And if you look at this, you don't have to look too hard. You can see a decrease with time, which would be totally undiscernible in looking at the fluxes. But as soon as you go into net transfer coefficient, it stands out. And that's what my current paper is going to be addressing. And can we address the reasons for it? I've lost, there it is, okay. Again, with this slight change in scale, we're now on a logarithmic scale. Expanded this thing out. Here's the 3C CDM in the dark blue. The confidence band around that. Also shown on the right-hand side. And for those of you who want to pay attention to honest comparisons, this is a factor of 2. This is a factor of 2. You can't adjust those and make that comparison. Here is the equilibrium solubility ratio of atmospheric stock, of mixed layer stock to atmospheric stock over this period of time. And you're seeing this decrease, which is due to diminished uptake, diminished equilibrium solubility of CO2 because the ocean is becoming more acidic. This one is what I get out of the model. That is diminished by the fact that it's coming out of the model, not the equilibrium number, but both are exhibiting the similar sort of behavior. Then I do what are called counterfactual experiments. Experiments in which I arbitrarily change a number and see what the consequence is. I can take the atmosphere ocean transfer coefficient, KAM, and set it equal to infinity, which would be an equilibrium. I can divide it by a factor of 2. And so those are what are shown here in the brown and the green. They likewise decrease. I can set the return transfer flux from the deep ocean to the mixed layer ocean. I can set it to 0. Is the decrease due to an increase in that return flux? Answer, no. So this is the kind of experiment that one can readily do and determine that none of those changes are responsible for the decrease over time and attribute it to the decrease in solubility. So now I'm drawing that horizontal line to show you what the net uptake coefficient would be if it were a constant. And then go back to the net uptake rate, and you can see the difference that's attributable to that decrease in solubility. I hope the referees can see that decrease. All right, I am going to skip this section. It's going to be another interesting paper. These are a bunch of models for uptake by the terrestrial biosphere. And what I'm doing is advancing, advocating a way to evaluate those models. And I'll come to the important results. A simple 3-compartment model with 2 observationally determined parameters accurately represents the uptake of atmospheric CO2 in comparison to observations and with state-of-the-art carbon cycle models, Transfer coefficient is a much better way to look at the data than that flux itself. This transfer coefficient has decreased appreciably over the past several decades because of decrease in solubility. And we'll skip the last one. Now I want to have some fun with some comments about models. And you may have heard this famous quotation attributed to George Box, the statistician, not Mr. Box who invented the Box model, but George Box, the statistician. All models are wrong, but some are useful. Example, this is a model that is wrong, but is useful. This is a model, ideal gas law, is wrong, but it's useful. And the question then is the 3C CDM wrong, but useful? Box goes on to say, since all models are wrong, the scientists cannot obtain a correct one by excessive elaboration. On the contrary, following William Ocken, he should seek an economical description of natural phenomena, continuum. Just as the ability to devise simple but evocative models is the signature of the great scientist, so over-elaboration, over-parameterization is often the mark of mediocrity. And with that, I close, and I'll pick your slings and arrows.
Thank you, Steve, for the insightful and beautiful talk. So
Your last conclusion offended the whole modeling.
everyone rises here, all the modelers.
That's right.
Yeah, well, you're absolutely right. And I'm focusing on the CO2 models, but this is probably applicable to the heat uptake models just as well, yeah.
Floor is
Malcolm?
open. I just
You're gonna call on people.
Yeah.
I would replace the word wrong because this is not correct. They're not perfect. Let's say that. Models are not perfect. But they use.
Neither is that very expensive watch.
Because ideal gas law is not wrong. It's not perfect.
I think this would be a lunch discussion.
Okay.
That's a very good point, Marat. I agree there in part. So we will talk that in lunch. Okay.
Well, thank you, Steve. Very interesting. A lot of the heat transport in the ocean is not just diffusive with exchange coefficient, but you see the deep Atlantic Ocean and the Antarctic bottom water formed during winter. There's a huge heat off in the Labrador Sea off Greenland, Iceland. There's a huge sinking to the bottom of cold, dense winter water, which then slowly moves towards the equator and uprises, and has a time scale of 1,000 years or more. So that's just the next step of your model to look at the effective processes in addition to the diffusive. My question is, can you use the pH of seawater to compute the content of excess CO2, or is it just not enough measurements? I mean, ocean acidification is a big problem.
Yeah, turn it around. And you've got at the surface ocean, you've basically got near equilibrium with the atmosphere. Could you go down in depth and measure pH better than you can do with measuring the CO2 by the conventional means? And I don't know the answer to that. My understanding is that the conventional means are the best. But Steve Beaufray might want to.
Yeah, there's a lot of sensitivities, but just straight up CO2 that's a pretty straightforward measurement. There are so many more.
The DIC.
Yes.
Yeah, but the normal set of measurements, I think, includes a pH measurement as well to constrain the set of measurements.
That's true, but it's not all. There are more measurements of just DIC than the couple sweeps. Yeah.
There's a huge problem. You can't get CO2 out of the ocean. I mean, people speculating maybe somehow could harvest the CO2 in the atmosphere and sequester it. But once it's in the ocean, it's all, there's no way to get it out ever.
Yeah, especially the timescales that are involved. And you said, the thermohaline circulations can be a long timescale. I don't treat to get back to your part one of your question, I don't treat the system as diffusive. I treat it as a simple rate coefficient times a difference in stops.
Yeah, but the physical mechanism, the turbulence mixing, that is the physical mechanism that's doing that. Well, simple exchange you talk about.
Basically, everything you're saying is going to apply identically to any other passive tracer, including heat.
Yeah.
So if I can use the measurements of heat uptake, which are directly measured from the Argos buoys, and they're gonna get better and better with time. Then I've got my proxy.
Understand.
All right, one last question before we head to lunch. All right.
No, it's okay. It's okay.
I just don't quite understand your argument about transfer coefficient change because of difference in solubility, Because transfer coefficient is a physical thing. It's it's basically turbulence exchange. And you just ignore there, like not ignore, you use it as a bulk thing, ignoring velocity of like wind. So it's one in there. But over the past 50 years or so, wind actually slowed down because circulation should slow down. So because of clutter basically require
This,
relative to evaporation. And so basically it could be explained just simply by weaker winds. So that's all.
the last issue that I raised.
Yeah, the change with time, like decrease with time. Could be just
Yeah.
decrease of wind with time.
Is it solubility or wind?
Solubility is
No,
already in the next term.
Yeah.
It's multiplied by that.
Yes.
Coefficient itself is a physical property. It's not, it has nothing to do with chemistry.
Well, if you're talking the mixed layer ocean, that's a pretty good thermal, chemical equilibrium. And I don't think that's the change, for example, in wind speed that's responsible for that mixing.
But it's in coefficient. You just wrote it like that, but in reality, it's actual non-dimensional transfer coefficient times wind.
Well, if you take the Weininghoff parameterization or something like that, it goes as wind speed squared.
It's not only one involved, it's just transfer coefficient.
No, not only but Weininghoff.
For fluid dynamicists, actually, your definition of transfer coefficients is bad, because that's not what it is.
Lunchtime.
Yes, I think we need a lunchtime now. So to continue. All right. In the front room, excuse me. Thank you, Steve.